This conference will now be recorded.
Great. This conference will now be recorded. Okay, guys. So, welcome to the first lecture. The course is called Model-Based Dependability Analysis for Mechatronic Systems. And this year, let's say, because of this current situation, I'm doing this online. And another thing, I'm now moved to Stuttgart. So I'm doing this course last time at TU Dresden. So I basically reusing the slides from the previous year. The main content is in the slides. It's basically PDFs that will be available on the website. So in the Opal system, and I can also give it to you by request if you are not registered. So, well, and one of the feature of this course that at the beginning of each lecture, I'm showing some videos, and usually it's about that something goes wrong or something fails, because we will talk about the dependability, and during today's lecture you will explain why. So do you see the video?
Yes.
Okay, great. So this is the launch of the heavy rocket. It's a Russian heavy rocket. It's called Proton M, and it was done in July, 1st of July 2013. So you can basically see the launch. It started. So I switched off the audio because it would be lots of screams and the bad words and so on. So, but you could see that already something goes wrong, right? So the rocket should not fly like that. So, and now something goes definitely wrong. So, and just wait for it. Boom. So, yeah. Now, let me try to explain actually what has happened. So, the thing is that in the space systems, and not only in the space systems, there are special kind of the sensors, and this is an example of the sensor, and it's called angular velocity sensor. And on this particular case, it was just a human error, because some of these sensors, they have been installed upside down. So, and it's really as a stupid thing which has happened. And this is a kind of example of a human error. So, and basically it was a payload of 3 analogous GPS satellites. It costed more than $200 million. So wait a second, I'm not sure that. Okay, do you hear me well, or there are some noises? Okay.
Well.
Okay, good. So, and the thing is that when they get out the log, they find out that the installation of these sensors was done by a young technica who has just employed some months before the thing has happened. So there was also the signature of the engineer who should check it, but probably nothing has been checked. So the thing is, on this center there is even an arrow that shows, okay, guys, this should be top, and that's how it should be installed. But nevertheless, the sensor was installed inside down, and there were even the pins that should got into the special holes. So, but nevertheless, so well, this was an example of a failure that can happen with a technical system. And at the beginning of each lecture, I will show the failures like this. So, and most of them, I don't know, by some historical reasons, most of them in this course would be from the space domains. So now let's come to the course, model-based dependability analysis for mechatronic systems. And basically, the first word which might have the confusion is the dependability. It has nothing to do with dependency or something. So in I think it would be the next time, it would be the second lecture. So, and dependability is a kind of the domain that studies the attributes like availability, reliability, safety, and so on, studies the errors. There are different type of errors that can happen in the system, and there is classification to the faults, errors, and failures. We will cover that also. There are also different meanings of these three words. And why we are doing it, to perform different basically to make the system more robust. So to perform fault tolerance, fault forecasting, fault removal, and so on. So the content of today's lecture is the following. So this is the name of the course, Model-Based Dependability Analysis of Mechatronic System. And what we will cover today, it is a model-based part and mechatronic system part. So on dependability, we will start it on the next lecture. And basically, we will start with the discussion: what is a mechatronic system, what is a cyber-physical system, and what is a safety-critical system, and why we need such kind of systems. And the second part of the lecture, we will talk about the model-based system engineering. So this would be the second part, and this would be the first part. By the way, do you see my mouse?
Yes.
Yeah. Okay, great. Okay. Systems, mechatronic and cyber-physical systems. Well, this is a classical definition of the mechatronic system. So I took it from the book of Professor Janczyk, and basically the idea that the mechatronic system is about the multidisciplinary approach. So it is a synergistic, spatial, functional, and technological integration of heterogeneous subsystems. What does it mean? It means that it is the system that consists of mechanical parts, which are here, of the software parts, so it's called information processing parts, which are here, and the information actually goes in between through the hardware. It's something like this is the hardware, like actuators that perform some motions, and this is the hardware as a sensors that senses the real system and provides information to the computers, to the brains of the system. And another feature of the mechatronic system is a closed action chain of feedback loop. So I mean, okay, the computer sends data to the sensor to the actuator changes the physical state of the system. The physical state of the system is measured by the sensors provide the information to the controller, and that's how a system works. User operates the system interact with the requirements. And usually the user and the environment is treated outside of the system. So, and here is an example. So all of you know what is a drone, or in this case, it is a quadrocopter. We have a controller set values to the motors provide forces to the airframe. It could be some environment things like a wind, and airframe sends sensors, like for example, inertial measurement unit understands the angular velocities and linear acceleration of the airframe, sends information to the controller, and also could be a user that basically observes the drone and operates it. So, but in the mechatronic system, user is also usually is treated outside of the system. And let's say if we make the system a little bit more complex, if, for example, we take several such drones and say that, okay, these guys now work as a network system, and they have a common task. They need to move this box from point A to point B. They are distributed, they are networked, and probably the human is also in the loop because the human is also considered as a part of the system. At this point, we already move from the mechatronic system to the cyber-physical system. So you could think about cyber-physical system as as a kind of the complex networked mechatronic system with a complex software part, possibly with a human in the loop. So, and that's kind of the system which we are using at the moment, which emerges nowadays. The term cyber-physical system, it was proposed in 2006 in US. There is a National Science Foundation, and basically the guys who gives money to the scientists, and the scientists, to get some more money, they come up, okay, let's create a new term, let's call it cyber-physical system. Let's say if we will call it mechatronic system or complex mechatronic systems, they will not give us money. We need to to brand it, rebrand it, and they call it just cyber-physical system and add new new properties for that. And now everyone is talking about the cyber-physical systems. So okay, and cyber-physical system is an engineered system that build from or depend upon the seamless integration of computation and physical components. This is also an important part. So, and another point of view is like, the evolution of the mechatronic system goes like from right to the left on this picture, because okay, at the beginning there were just mechanical systems, then we start have some electronics and it becomes electromechanical systems, and then we add some software and it becomes the mechatronic system. And from the cyber-physical system, the origin is quite opposite. It's basically a kind of it's a point of view of computer scientists to the real world. And they basically, put the information technology as a core thing, saying, okay, this is the brains and everything else is just, something which, serves to these brains. And this is basically the movement from the left to right. So CPS originate from the information technology domain. So a strong focus on the software, and as I told, communication, the system is distributed and so on. So such kind of picture, I take it from this website, it's cyberphysicalsystem.org. Not exactly, I updated it a little bit. So, but here is basically another explanation, what is a cyber-physical system. So cyber-physical system in blue, we describe these distinctive properties. So it is a feedback system, real-time, intelligent, adaptive, possibly with a human on the loop. It is a heterogeneous. Heterogeneity means that it incorporates different kind of components which are really different from each other, like mechanical parts, mechanical physical parts, sensors, computing hardware, software, and network. Network, physical parts, hardware, and advanced software. So the applications, let's say, now it is applied in any high-tech domain, let's say, so in space, in industrial automation, in healthcare. It's usually, it's even on these domains, it's usually about the robotics. So like, for example, some medical robots, it's an example of the cyber-physical system, or autonomous car, or the fleet of the autonomous car, it's also a kind of a cyber-physical systems. And because we do this shift of the paradigm from the mechatronic systems to the cyber-physical systems, there are new requirements, which we can also call challenges. And in order to design such kind of the complex system, we need to have a better design methodologies. We need to be able to cover all of these domains, and somewhere on the top level, we need to group them together to design the entire system. So we need to take into account complex interaction between the different components. We need to take into account timing. Everything should be timed when we expect the signal it should be received, and the things like this. Of course, it should be scalable because, for example, we could add new components to the system. We need to be able to scale the design. And we also need to be able to analyze it in, let's say, in early stages of the development. This is also important like when we create some first design of the system, we already need to make some analysis in terms of the future performance or the future reliability of the system. If we can do it in early stages, it will save us time and money. So now about the requirements. Security, the system should be secure, it should perform well, and this is the word which we will cover on this lecture, is dependability. So, and I will talk about reliability, that the system should perform the function well, and safety, it means that it should not harm the user or their environment. Okay, so and this is possibly my last slide about the mechatronic system and cyber-physical system. Here is some comparison, which I also took from this paper. So there are lots of similarities between these terms, but let's say the cyber-physical systems, it's like, you know, like the mechatronic system on steroids. So with adaptive structure, decentralized organization, possibly distributed geographically, human in the loop, functionally open, large community, real-time processing. Okay. Another terms which usually you could see around the term cyber-physical system is as follows. Industry 4.0, it's basically the application of the cyber-physical system for industrial automation. Like the robots in the facility, they are distributed, they are interacting with each other, human to robot collaboration, human in the loop, and the things like this. System of systems, it's another concept. It's basically the idea behind is that we create the system of systems, and the idea that we group the systems together, and together they will achieve better performance as separately. So this is the core concept behind. And of course, Internet of Things, the network of physical devices, vehicles, blah, blah, blah. Other items embedded in software, sensors, actuators, and connectivity, which enables these objects to connect and exchange data. So these terms are connected to the cyber-physical systems. Now, the thing is that half of the applications which I talk about here, they are so-called safety critical. It means that if something will happen during when you are driving your car, flying your plane, or if you are under the operation, under the surgery in a healthcare facility with this robot, your life will be endangered. And such kind of systems, they are called safety critical system. So a safety critical system is a system whose failure or malfunction may result in death or serious injury to people, loss or severe damages to equipment or property. But usually the guys are talking about the severe injury to the people. So this is the key point. Such kind of system we will call safety critical systems. So here is the literature which we have used on this part. So, and this is all for the, I hope that I give an overview about what is mechatronic system, what is cyber-physical system, and what is safety critical system. So, and with that, I plan to move to the second part of the lecture, where I will cover model-based system engineering. I'll tell what is model-based system engineering and what kind of models we could use. Okay, this is the first lecture, and basically we are talking about the terminology, and here I also will start with the terminology. So let's say if you start Google something like model-based, you could find a lot of terms which are really similar, and basically with this triangle, it's a kind of thing, and you could start with the word model, then you could use, for example, as a based or driven, that you could use software system, and then you could use one of this word, and you will get some legitimate term which means something, like, for example, model-based system architecture, or model-driven software design, model-based system testing, and so on. So, and there are, you know, there are really lots of acronyms which you could find: model-based engineering, model-driven architecture, model-based system engineering, model-driven design. All of the things, they mean something, and in different communities they are used sometimes with some, ambiguity or confusion. So this example shows, let's say, one of the classification of these terms. This is more or less, accepted classification, but you should be careful when you will be in the industry. In this particular company, they can call it exactly opposite, and if everyone understands what we are talking about, it's fine. I'm just giving you some examples. So let's say the most general is a model-based engineering. Basically, we use models as an integral part for technical baseline. So we use models to define the requirements, to perform the design, verification, and so on. Model-driven engineering is a software development method. It is a kind of that we create as a model, and then using this model, we maybe in automated way, like with AutoCode, we create the software. Model-driven development is a little bit more narrow MDE, which are used in some companies. And for example, model-driven architecture, it's a very special software design approach, which is produced by the object management group. So, well, in our case, what we will talk about, the model-based system engineering in a very general sense. The idea is following. I want to develop a system. I have an idea. Using this idea, I create models. Basically, I using some kind of modeling tool, or even it could be, pen and pencil. I draw some boxes connecting this with arrows, and I get something more formal. I basically just put the concept from my head and I put it either in the paper, or I'm using some tools to draw some structures of my system, and these are the models. And then using these models, I can automatically or semi-automatically create the system. For instance, if I create a model of my system using a Simulink, I can click a button and auto-code the Simulink model into my controller. Or in some more advanced ways, really in some environments, now I can create a model and start my 3D printer and get the system. Okay, even the physical things can be, let's say, auto-coded or automatically implemented. So, and what we will talk about, these are for us model-based system development or model-based system design. We are using the models to create the system, nothing else. So in the more broad sense, it's usually when you get the system, after you got the system, you need to test it, to measure some performances, and to get the requirements, to compare the measured performance with the requirements, and probably improve the models. And this we will call, let's say, model-based system design in a broad sense, which such kind of. So this also confirmed with so-called V model, which is really okay. So nowadays in industry, for example, in automotive industry, everything, all the life cycle of the system is done with so-called V model. So the V model, here we start with the concept of operation, we define the requirements, we create the design, then when we implement the system. Usually here we separately implement, for example, hardware and software, and then we start unit tests. We test the unit separately, then we create the integrated test and so on. And finally, somewhere here we should have the product. The thing is that nowadays, let's say, such kind of paradigm, it becomes a bit obsolete, because the system becomes more complex and they are modifying. For example, you buy your Tesla car, and then after a month you get a software update, and where we are here, we already got the product, but what this update means, should we start a new one? So it's a little bit different. So, and basically we are switching to such kind of a spiral environment. So we get the system, we check it, we update it, we got the system, and so on. So this is a kind of a life cycle. And how we define it? Model-based system engineering methodology that focus on creating and exploiting domain models as primary means for information exchange between engineers rather than document-based information exchange. Okay, so long story short, we are using the models for the development, and this we will call model-based system engineering. Okay, here we are developing the models, and we want to model cyber-physical systems, which I talked about before. For a complex cyber-physical system, I cannot just use my pen and draw something. I can start with that, but later I have to put it into some structured way. I need to define the use cases, I need to define the functions, I need to define the structural blocks of the system, I need to define data flow between the structural blocks, I need to define the hardware, I need to define the software, I need to define the deployment of the software to the hardware, and the things like this. For that, I need some kind of the modeling language or modeling tool. And in order to perform such model for cyber-physical system, this tool should be able to support high level of abstraction to model heterogeneous components. I need to be able to model, okay, this is my controller and this is my actuator. This is a physical part and this is a software. I need to be able to model them together. It should be standardized because probably I will have a big team, and my engineers who develop the hardware and software engineers need to be able to work in the same environment, so we need some standardization. And of course, I need to sell this system later, and that's why I need other kind of standardization. It should be, for example, safe. So because if I want to sell some, special block to BMW or Audi, I need to certify it according to some special standard, particular ISO 26262, and only after the certifications the BMW will buy it and put in the car. So that's why it should be certified. In the best way, it should be automated, like I want to have the autocode here. I need to be able to express the ideas which I want. I want to say, okay, these are cycles, these are loops, these are things like this. And it should be unambiguity. Unambiguity means that if I design something, another guy should understand it exactly how I planned it. It shouldn't be like 2 or 3 meanings of the same things. Okay, so here are few examples of the model-based system engineering methodologies that we could use. Structured analysis, it is a kind of an old method for the model, for the modeling. There are actually lots of the methods like that, and I'm just using this as an example. So nowadays it's not used very often. Basically, you might use it if you design something small, or if it is, the first step, some draft design of your system. There is let's say, the big community around unified modeling language, UML, probably heard about that. And there is also a profile which is based on top of UML. Okay, UML was designed first for this. Okay, UML is a very general thing. You can design business processes, you can design software, basically whatever you want. And then the guys, specified for the system development, where you can design hardware, software interaction, things like this. And this thing is called SysML, systems modeling language. The third part, I will not cover this a lot because probably you are using it on some other lectures and courses. It's MATLAB, Simulink, and Stateflow. This is also a kind of the model-based system engineering paradigm. But I will talk about another thing. It's called Architecture Analysis and Design Language, AADL. So, and in our exercises, we will basically cover UML and AADL, SysML and AADL. So, and in your first exercise, we will design a mechatronic system using these languages. Okay, now I plan to spend some time explaining, let's say, 3 of these paradigms. I will not, we'll see, let's go. So, we started at 10, yeah. It's fine. So the structured analysis. In the structured analysis, basically we have a functional view where we define the function of the system. For instance, the function of the controller is controlled altitude. The function of its sensor is generate torques, and the function of this, like the frame, is to move the satellite on orbit. There is another view, it's called control view. It's, for example, it's a kind of a state machine that describes the states of the system or the states of the software. It's called the like standby, off, nominal operation, and there are jumps between the state. And there is also hardware software architecture view where we can, specify the hardware components and we can specify the software components, how they interact. So there are some standards that describe the structured analysis, and in some companies they are still used, but I will not really focus a lot here. I will better jump to more general, not more general, but more, let's say, well-defined or developed paradigms. And I will tell about the UML and SysML. So, and here is some examples of some UML and SysML diagrams. And these diagrams we used to develop this bird. It was a quadrocopter, it was octocopter, 8 motors. And we used, for example, SysML diagrams to develop the hardware. We used UML components diagrams to develop the software and deploy it on the hardware. And we used a special kind of behavioral diagrams, such as activity diagrams, to describe the mission phases, for example, and to describe the software behavior. Okay, so and the second paradigm, it is AADL, and in the AADL, for instance, it is a little bit more specific than SysML. So, and in the AADL diagram, you could also design the hardware, and you could also, like devices, memory, buses, processes, you can design your software and you can perform the interaction between them. So UML SysML, basically you are drawing things, and in the AADL it has a visual model, and it's also has a code model. Like, for example, if you create, it is like with a code, you could see this picture, or you can draw this picture and it will generate you the code like this. And this is, let's say, the AADL is a little bit more specific and more structured, and that's why there are so-called analytical capabilities. So you can analyze these diagrams well. And there are tools like, for example, Osate. It is a UI to create the things. Ocarina, it's a code generator, and Taste, it's a complete tool chain. I'll talk about that later. So Stateflow, Simulink, it is other paradigm. MassWorks, they are trying to conquer the world, and they are developing let's say the Simulink and Stateflow, it's even more specific. It's usually we are using it to design either the controllers, or we also using to the prototyping of the entire system when we are designing the control and designing the physical system. Simulink supports the AutoCode well, and also Simulink is very good for the signal processing design. So again, this is our simplified system development lifecycle. We create the model, and in order to create the model for the cyber-physical system, the models could be either in UML, SysML, MATLAB, Simulink, or AADL. Some of them performs even partially automated system implementation. Actually, nowadays in the industry, there is no question about the model-based or not model-based development. Everything is model-based. The question is how good or how automated is your tool chain. In some companies, it is, let's say, more automated and more strict, and other companies, it is less strict. If it is a small company, usually you want to develop the product, you are not really, focused on the on your tool chains in the companies like, like Siemens, ISA. They are doing it in a more, let's say, I wouldn't say professional way, but more strict way, and they're using they're using the special environments. Okay, sorry about that. Like there is a Simulink systems PLM software. There is a taste which is used in the ISA and so on. Okay, now let me talk about UML and SysML in details, because we will use it in the exercises. I will start with UML. General purpose development modeling language. It was emerged from the software domain. First, it was used for the software design. It is a standard way to visualize and design the system. There is a company, or it's not a company, I mean, it is a group of professionals, object management group, and these guys, they develop these standards for UML, and they publish them as a specification in their website. And I have to check, but at least last year, the last version was 2.5.1, and it was published in 2017. So one of the point of view how you could see the UML, it is a number of the diagrams that you could use to describe your system. The diagrams are grouped into two groups: behavioral diagrams that describe the behavior of the system, how the system is changing in time, and structural diagram. It is static. It describes the structure of the system. So with the blue boxes, I highlighted the diagrams which I will talk about and which, according to my knowledge, are used in the most cases. So about the structured diagrams, there is class diagram, component diagram. Class describes the classes of your software or the classes of your system in general. Component diagram describes the components. There are also object composite structure deployment diagram that describe, like, when, for example, software component is deployed on the hardware. This we will do on this one. Package diagrams, when we need to package something. Profile diagrams, it's a special case, we will not cover that. More interesting is the behavior. In the behavior, there are several diagrams like use cases describing how the system can be used. State machine, if our system operates in several nodes or states, we can draw a state machine diagram. And activity diagram, it's a special kind of the diagrams, a little bit similar to a state machine, but I'll discuss it later. And there are also like sequence diagrams, timing diagrams, communication, and so on. Well, if you want to learn UML better, I could recommend the website umldiagram.org. I talked with the guy who is developing this website, and he provided me these diagrams to use on this lecture. And basically, there are lots of good examples there. So from my point of view, it's the best place to learn UML. Or yeah. Okay, the first kind of the diagram is use case diagram. It shows how users can use their system. These are the users, they're called actors. This box is our system. These circles are the use cases. For example, the user could view items in some online shopping, or could register a client, and so on. So it also shows how the users can collaborate with each other. And there are some special kind of, UML about the shapes, like, boxes, these ovals, or ellipses, or, and about the lines. And different kind of lines have different meaning. For example, this line, just black solid line, it just shows that this actor interacts with this use case. But there are other lines where we have, arrows, and we have some text here. And for example, these basically mean that the use case make purchase includes view item and includes checkout. Basically, this is, some hierarchy of the use cases. So, and use case diagram is the most general UML diagram. So if you start designing something, if you start designing the system, the best way you first specify what a user can do with the system. And this is your functions or your use cases. And this is the diagram you are starting with. So, and also usually the diagram for such kind of description is not enough. And for each use case, you need to describe so-called fully dressed table, or like a fully dressed, I mean, it means like you extend it and you add additional information for that. And for each of the use case, you describe the name of the use case, the scope, the primary actor, preconditions, postconditions, triggers, and so on. So important to know that in the use case diagrams, there are basically two kinds of arrows, or they call it relationships. So, and there is include relationship and extend relationship. What's the difference? Include relationship can be used to simplify a large use case by splitting it into several use cases. It can also be used to extract common parts of the behavior of the system, I believe. So, for example, checkout includes a scan item, calculate total and tax, and it includes payment. Extend is a direct relationship that specifies how and when the behavior defined is usually supplementary. So it's usually optional. I mean, this means that checkout consists of these parts, and this part cannot be, cannot be used separately from the checkout, or the checkout is not complete without this part. In this case, it's vice versa. It's like an optional thing, like get help on the registration extends the registration. It means you could do the registration and you could separately get help on the registration, but usually it could be a use case when during the registration you also get help. So that's the difference, and for some particular things it is important. Okay, second type of the UML diagrams, class diagrams. These diagrams are used in the software a lot, and I believe 90% of the usage is software. However, you can describe your system or even your company or whatever, so some entities. And the idea that basically you are describing the classes with these boxes, and in each class has a name, like for example, book or author, and the class also has attributes. For example, author has two attributes, name and biography, and the book has other attributes like ISBN, title, summary, and blah, blah, blah. So, and in the class diagrams, we use several relationships. It is associations, generalizations, and dependencies. Okay, the generalization, it is about the, okay, just a second. Yeah, so the generalization, it's basically about the inheritance. So it is binary taxonomy. It means it is direct relationship between two classes, and between and it is a relationship between more general class and more specific class. For example, we could have a class in account. It is a general class, and we have an exact class, let's say, or more exact or more specific class, checking account. So, or for example, here we have a book and we have a book item. And the thing about that is that if the book item is a specification of the book, it will inherit the attributes of the book, plus it will add some of the attributes which this class has. Okay, then there are two kind of aggregations. and they are denoted with the arrows like this with these diamonds, and the differences: in one case the diamond is solid, and in one case the diamond is black, and in one case the diamond is white. What's the difference? Composite aggregation, or strong form of the aggregation. It means that a part could be included in at most one composite. If a composite is deleted, all of its composite parts are normally deleted. I mean, for example, hospital consists of departments. And here you see these numbers, like, for example, 1 and 1, 2 dots, and the star. This means that one hospital consists of one or more departments. And the department is a strong part of the hospital. It's something similar, like, you know, like includes here. So it means that if we delete the department, we still have hospital, but if we delete the hospital, it means that we have to delete the departments. So another thing is shared association or shared aggregation with white thing. So, and in this case, it means that a big form of aggregation and shared part could be included in several composites. I mean, if we have a department, it is a department of exactly this hospital. But for example, if we have a triangle which consists of 3 segments, we could have another triangle that share one of the segments, and it means that one of the segment could be a part of this triangle and another triangle, right? So, and this you could see, like, for example, multiple triangles can contain 3 segments. Okay, this means multiple triangles, and this also means that one segment can be a part of several triangles. I hope this will make sense. So we will do some exercises, and it will be a little bit more simple. Okay. The next part of the UML is UML component diagrams. So, and in the component diagrams describe components and how these components can be connected. And the component is some part of the system that can be, you know, take out of the system and maybe reused in another system. This is the idea of the component. And the main idea of the component is that it has interfaces, like provided interfaces and how it's called, provided interface and required interface. So if we have a component and we have other components and the interfaces are okay, we just connect them. If we have another system that has the same interfaces, we can take the component from one system and put into another. And such kind of things we can model with the component diagrams. It shows components, provided and required interfaces, port relationships, used in the component-based development to describe with service-oriented architectures. The constructed components could be reused. Components could be replaced by some other equivalent or conform components. Let's say if we have a component in the car and we have a new one, we need to be sure that the interfaces are the same. Here is an example of the component diagram. It's again, I took it from this website. There is a web store, and the web store requires the warehouse through the special interfaces, and the web store requires the accounting through the interfaces like manage orders and manage customers. And the warehouse also requires, the warehouse provides the interface for the accounting. The difference is, for example, here, do I have a special? No, I don't have a special slide for that. The difference is, let's say, with such kind of arc like this, we are modeling required interfaces. And with a circle, we model provided interfaces. And in order to components to, to work together, it should be the connection. Let's say the provided interface should go into the required interface, okay? There are dependencies between the interfaces. It could be the sub-components inside. It could be the delegation connection when the sub-component interface goes outside of the system, but basically it's quite straightforward here. Okay, these diagrams, class diagram, component diagram and use case diagram. These are examples of structured diagrams. It is a structure, it's static, nothing to do with behavior or action. Now we jump into the behavioral diagrams, and we will start with activity diagram. Activity describes the actions of the systems, and activity diagram shows flow of control and flow of objects. Let me explain it. Basically, we describe some process. This black dot means that we start here, and this black dot and around means that we finish here. So these black lines mean that from the start we jump to this action, and the first action is receive orders, and in order to execute this action we also need an object, request order. If these two things, if we start it and we have the request order, we can execute this action. After that, we jump into so-called fork, and this is the fork of the control flow. Okay, and depending on some parameters that are usually written on these arrows, like either order is accepted, then we jump here. If order is rejected, we jump here. It is important that each action has only one control input and only one control output. It means that after the forks, we need to have also join. So we need to have a join to, and then let's say either we come from here or we come from here, we go to the close order. Okay. Then activity diagrams also allows the modeling of parallel processes. And for that, we are using forks or merges. It means that after the filling order, at the same time, we start send invoice and ship order. Send invoice, we create invoice, it goes to the access payment, we execute access payment. When access payment is finished and ship order is finished, then the processes are merged and we jump here. The difference that here it is or, we are going either here or here. Here it is and, we are going both here and here at the same time. You could think about it like, like a token. If we put a token here, the token goes here. Here it goes either here or here. If we go here, then the token is split into two tokens. One goes here, one goes here. And here, in order to go further, we need to wait until both of them. And this is a kind of, such kind of things are usually used for the synchronization. For instance, we have here another activity diagram where we have a driver, brake system, and ABS, and these are so-called lanes. Sometimes in the activity diagrams we are also using the lanes to describe that, okay, these activities are the activities of the driver, these activities are the activities of the brake system, and these activities are the activities of the ABS. And this driver, brake system, and ABS we can design using our class diagram. We have a class driver, we have a class ABS, and so on. And then here the driver turns the key on, then we have a parallel activities. The driver is doing the driving, the brake system doing the braking if necessary. Actually, the braking system waits until the driver presses the brake pedal, and when the brake pedal is pressed, the brake system does the braking. So, and some enable, let's say control operation enables, and some brains understand should we switch on ABS or not. Then if we need to switch on the ABS starts the motion traction and helps to the braking. And the system, and there is so-called interruptible region, because this is an interrupt. When the driver can do an action like key off, the system will be shut down. Basically, we jump out of that. That's the meaning. Here is another example. This example we will cover a bit later, but also we could see we start, we have parallel processes, and here we have the control loop where we are jumping. Okay, and these were activity diagrams. And the second behavioral diagram is state machine diagram. It's a little bit similar to the activity diagram, but different. UML state machine is significantly extended realization of the mathematical concept of finite automata. It should be automata here. Okay, in the state machine, we describe the states of the system and the transition between the states. This also means that we start here. We start in the idle states, it means system is doing nothing. Then with a service, we could jump out of service. If it is fixed, we jump here back. And yeah, this is a bank, this is a Geldautomat, the ATM. Let's say it could be that we need to service it and the serviceman comes and the bank ATM is out of service. And if a user comes, they should insert a card and the ATM will be in the active state. And then either because of the cancel or done, we jump back. So what's the difference between the state machine and activity diagram? Activity describe actions, and action is something which has start and which has an end. It is something which we can done in some, okay, I would say that it's something that we can do on a, rather fast, do something, send documents and so on, or so on. But the idea, it's not about the speed. It's about that we assume that this is a kind of the job that has a start and has an end. In the state machine, the system could be in one state infinitely long. We can just state on this state and this is okay. It doesn't mean a deadlock or something. For example, if our car is staying in the garage, it is in the idle state and it's fine. So it will stay there until we do something, until we start the car. So, and that's why for each state, we have 3 behaviors: entry behavior, do behavior, and exit behavior. This means that we start when we enter, and actually these behaviors can be described with the activity diagrams. And when we enter the state, we execute enter behavior. When we are in the state, we in a cycle execute do behavior. All the time we are in the state, we run this do behavior in the cycle. When we are exiting, we execute exit behavior. Okay, so it could be the composition, like the state could have a substates, and it's also possible to model parallel states using the construction like this. So it's also forks and also joins, and inside we are using like this dashed line. It means that these states are, the system are both in this state and this state at the same time. Okay, so, and here is a composition. For example, we have the state, here is a state machine, and it has state 1, then we jump into state 2 or state 3, and then we jump into the final state. So, and each state we can describe with an activity diagram. For example, during an entry, we run the action A. When we are inside the state, in the loop, we are running actions B and C, and we are getting out. When we are getting out, we are running the action D. Okay. Another kind of the activity behavioral diagrams, I will not stop here, but I just want to highlight that there are more behavioral diagrams like sequence, timing, and even more. So, and the examples are shown here. This one is a timing diagram, describes the time when the system executes something. And there is also a sequence diagram. And sequence diagrams are usually used to explain the exchange of the messages or data or signals of the system components or system classes. It's like, for example, a user sent invoice to the web browser sent request to the application sends something back, we send something to the authorization sends something back, and then we send something back to the user. It's also could be like ifs, like this alternative, it means like when we are going here, we either do this part or this part. So it's other point of view on the behavior of the system. And with this, we are usually describe some specific routine which we are doing with the system, and it's basically based on some message exchanges. So far so good. Let's go further. We have UML is a big thing, but it even can be further extended. So we could use UML profiles to add into the UML some new information which we're interested in. Okay, so like in the UML, there are classes diagrams which consist of the classes and so on. There are activity diagrams which consist of action and so on. But with these stereotypes, stacked values, constraints, with this extension, we could even add some special blocks, or we can specify like, okay, this class, it is some our class which we can use for something. We could even create a new kind of a diagram using such kind of extension mechanism. So it's really it's really customizable thing. You could, adjust UML for your needs. And for that, there are a number of profiles. Yeah, for example, we can have a class which describes a part of the system, and we can specify a stereotype. We can say, okay, this class is faulty. It means that this part of the system can fail, and we can define the probability of failure. And this could be already inside the UML, and we will just click a button and say, okay, this class is faulty, and the probability of failure is 0.0001, for instance. Okay, like the probability of failure of this controller. So there are some examples. For example, there's Martha profile, modeling and analysis for real-time and embedded system. And there is, for example, also DAM profile, dependability analysis and modeling, which is more related to our lecture. And in this profile, using the UML means, we describe our faults, errors, failures, and different mean time to failures and so on. And then we could use these examples like I've shown here. We can say, okay, this component is faulty, and we can specify the probability of failure, mean time to failure, and so on. Later, we could use this information to compute the reliability of the system, and I will show it later. So another thing I told at the beginning, it is a SysML. It was a UML, and then the engineers take a look into the UML and say, okay, interesting tool, but it is too general. We want to design an exact engineering systems. Let's create a profile that will specify, make the UML more narrow and that we could use for the design of engineering system. And they developed SysML. It is also now official profile. You could find it on the same omg.org. Stable version of 2017, but I have to check. Maybe it's already something newer. So, and it basically takes UML, removes some diagrams, adds some new diagrams, and changes some diagrams. Blue diagrams like package, sequence, state machine, use case are exactly the same as UML. Activity diagram is modified. Like block definition diagram replaces the class diagram. Internal block diagram replaces composition structure, and there are even some new diagrams for describing the requirements and parameters. So basically, they took very general UML and make it specific, and by this specific thing, you now designing not like the web services, software, some very general system. You're describing the technical system. Like, for example, here we have a diagram of the distiller. Okay, I will tell about some diagrams of the SysML. I will start with the block definition diagrams, because the design with SysML, okay, we started with the use case diagram. We describe what the system will do, but in the next step, we usually start describing the block definition diagram. And here we describe what our system consists of. And this block definition diagram, or I will call it BDD, It's a black box representation of a system. It describes a hierarchy like distiller consists of the heat exchanger, boiler, and valve. And it includes blocks from any type like software, hardware, physical parts, like suits for our cyber-physical system. And in comparison with UML, the SysML BDD redefines the class diagrams by replacing the classes with blocks. This is basically blocks, the same like classes in the UML, but more specific. Again, here we have a distiller. As you remember, this we have how it's called, composite aggregation. It means that hospital consists of the departments, and our distiller consists of the heat exchanger, boiler, and valve. So, and we also have the numbers here. It means that one distiller has one valve, which is a drain for the distiller. It has two boilers, which is evaporator for the distiller, and it has one heat exchanger, and from the distiller point of view, it is a condenser. Okay. So the same, for example, we have used here. We describe the hardware components of our octocopter, like several computers and several sensors. Okay. Yeah. So for example, this is a SysML block definition diagram of this quadrocopter. We have a system that consists of the ground system and flight subsystem, and the flight subsystem consists of two computers, 1, 2, 3, 4, 5 sensors, 8 actuators because of this number 8, which is very small here. So, and we could see that all these sensors are generalized as a class sensor, and for example, this is generalized as a class actuator, and so on. Okay. Well, the next diagram is internal block diagram. Like with the block definition diagram, we describe the hierarchy. Distiller consists of this, that, and that. With the internal block diagram, we describe how these blocks exchange information, or exchange values, or exchange some messes or whatever. So provides a white box, usually instantiated from the block definition diagram. Composite blocks for the BDD are instantiated from the IBD parts, and so on. I better explain on the example. We have a distiller, and we have an input, like the water comes as an input. And this water, or no, it's not the water, it's a heat. It goes into the boiler, as well as the fluid also goes into the boiler, and then boiler produce the residue to the block valve, and if the block valve is open, it produces a residue outside of the distiller, and also the water from the boiler goes to the heat exchanger together with the water, the cold water, which comes from outside, and then some part goes here and some part goes here. The idea that we show how and this could be like, physical flows of the water, or it could be the currency, like for electrical system, or it could be the signals or data for the computer systems, or it could be something in between. So it's up to you what you will send from this block to that block. Important that you are using this line, and you're also using the ports. These small things, it are the ports, and for example, you could have another valve which is connected to the same port. Okay. For example, here these are basically either signals or currencies. Like for example, FPGA module sends engine commands to the engines, and the camera receives the triggers from the navigation computer, and when the trigger triggers the camera, it sends the data, basically the image, which is called strobe, to the FPGA model. Okay. So, and here on this example, I'm also showing, let's say UML and SysML, they have the same nature, so we can mix them. And here we use, for example, UML component diagram to describe the software components. Okay, now about UML and SysML tools. There are commercial tools which are quite expensive: Rational Rhapsody, Magic Draw, Enterprise Architect. In industry, most of the cases it's used Rational Rhapsody. Magic Draw is more used for academical purposes, but there is also a good free tool which we'll use in our exercise. It's called Papyrus. Important that there are more UML tools, but only some of the UML tools support SysML. And from the free tools which support SysML, I found Modelio and Papyrus. I used both of them. My choice is to the Papyrus. It's more stable. Modelio is not so stable. Okay, this is a small cheat sheet which you could use. Here's a link to that. And basically that's all about the UML SysML which I have today, and probably I'll go to the final part of the presentation. It's about AADL. AADL, it's another design language. Originally it was called Avionics Architecture Description Language because it has started from aviation. I believe in Boeing. However, now it becomes more general and it's also used in different industries. And basically, the standardization is now done by the Society of Automotive Engineers. So they are standardizing AADL now, and that's why now it's not avionic architecture, but it is architecture analysis and design language. Okay. Also, there is a website where you can find the current state or the current specification of the AADL. AADL has 3 views: textual, graphical, and you can also save it in the XML format. Actually, UML and SysML you could also save in this XML format. So, but here, and usually when you are using the AADL tools, they have 2 views, and you either, model your system as you program it, and then they create the graphical representation, or vice versa. You can also draw and then this appears on the textual. They are, synchronized. Well, sorry for the mess in the slide. Architecture analysis, AADL. So AADL allows to, okay, there is a very good book of this filer, so where you could read about AADL much more than I'm telling today. So with AADL, you can model hardware and computing hardware such as processors, memories, devices, buses, and then software parts like threads, data, processes, subprograms, and thread groups. So, and the components are grouped into the groups like application, software, data, process, thread group, thread, subprogram, platform, device, memory, bus, processor. Everything could be put into the packages and can be composed into the systems. Okay. Here is an example. We have a Mechatronic system or cyber-physical system. It is it is a kind of a medical patient table, which can be controlled by a user with a joystick or with an HMI. And on the top level, we design the hardware. There is a controller that sends data to the HMI and receives data from the joystick. And there are driving unit, and the controller sends the data to the driving unit and receive the sensor data from the driving unit. And the software of this controller we describe with this software diagram that consists of several threads which are basically running in parallel. And here we could see the sample times, like there is a joystick which is read each 100 milliseconds, and there is like control routine that is executed each 10 milliseconds, takes information from the kinematics and sends information. Basically, this is what's going on inside here, but from the software point of view. Yeah. And if we take a look on the textual representation, we will see something like, okay, we have thread, joystick thread. It has input data port, output data port, input data port receives I reference linear velocity and sends just reference linear velocity. And there is another, and this is a kind of a class, and in order to initiate it, we need to create an instance of the class, and that's why we create the joystick implementation. And in this implementation, we can specify the timing parameters. We are saying that, okay, this routine is executing periodically. The period is 100 milliseconds, and it takes from 0 millisecond to 1 millisecond time. If it is stuck and executed more than 100 milliseconds, it will be, cut and rerun. And there is special parameters called chatter property. And for example, there is a priority, and this priority is used for instance, I told before that AADL is also used for analysis. And for example, there is a tool Chatter that performs timing analysis for the AADL models. And basically, if I will create an AADL diagram where I have two producers that send data to one consumer, and I specify like this thread implementation, like, okay, these two are periodics, and I define the periods, I define the deadlines, I give the priorities, the Chatter will it's actually will do this. It will create a schedule. It will define when, because these threads are executing on the same computing unit, and it basically creates a schedule, and according to this description and according to a special protocol, the schedule will be the following, like first we run the producer 1, then we run the producer 2, then we run the consumer, then we run the producer 2 again, and so on. So, and this is done automatically. So you can just create the system, and you could analyze and see how it will be, scheduled for your processor. And you could analyze, let's say, are your timing okay or not? Well, similar to the UML, AADL also can be extended with user data. And in the UML, there were stereotype, tagged value, constraint, and with the stereotype, we can add special information like probabilities of failure, or for example, mass of the part or something like that. Similar can be done in the AADL. There are so-called annexes. Annexes are something like profiles in UML. There are annexes in AADL. And there are also property sets. So language annexes, call language, blah, blah, blah. And for example, what's important for us, there are error model annexes, specified faults and propagation concerns for the AADL diagrams. So about the tools, there are several projects for the analysis of the system developed with AADL. There is TASTE, and there is also Compass. And for the modeling of the AADL, in 90% of the cases, one tool is used. It's called Offset. It's based on the Eclipse and the special plugins. And there is another tool called Carina for generating of the code from the Offset. So in our exercise, we will use Offset tool to create one AADL diagram, basically. Okay, so long story short, let's closing the lecture. I just want to tell again, we have cyber-physical systems. We need to model them. For that, we could use several types of the modeling languages, including these 4. There are some, some simple paradigms. They are simple, good for high-level functional design or small and fast prototypes, but they are not powerful enough for complete design of complex systems. Usually they don't have auto code generation. UML and SysML, a very big thing, covers all phases of the system development lifecycle. You could create use case, you could define requirements, you could define the design, you could even do auto code. Lots of tools, some are better than the others. They have extension mechanisms like profiles. The code generation is possible, but it's not the main idea of UML and SysML, but it can be done by some third-party tools, which are, from my experience, rather poor. In the UML, it is relatively complex. I mean, to start, let's say, if you start the new project, it is another project to learn UML. So you need to understand how it's done and so on. Let's say you need first to learn UML and then use it. So that's why it is relatively complex, and sometimes it's too general. UML is nothing else as a set of the modeling tools, and you could do whatever you want. How you use UML, it is other story. In each company, in each community, there is a way how and what kind of diagrams you are using. And when you are starting, sometimes it's too general. They just giving you a tool set, come on, well, what I can do with that? Give me some guidelines. So it's not enough to have UML. You need to have the guideline how to use it. MATLAB Simulink and State Flow, probably you know it. It's good for embedded control systems, it's good for fast prototyping, it's good for signal processing. Basically, in the Simulink and State Flow, you are not modeling, you're just developing through the modeling, right? You create the blocks and then you already can autocode, you can run the system, you can get some parameters already. Here you just modeling, you describe the system, and here you already get some executable system. There is also executable UMLs, but it's also kind of a third-party things. It's far from the Simulink and State Flow. So there is native autocode, and Simulink and State Flow are used in the industry a lot. Like according to my knowledge, most of the automotive industry now is auto-coded from Simulink models, but they are not using the Simulink blocks, they're using their own blocks, but they're using the Simulink and DSpace to glue the things together. Like Audi or BMW or Volkswagen, they have their own block sets, which they're using for different kinds of the controllers, and they're using the certified code generators and certified hardware, and the tool chain is automated. You create the model in the Simulink, or let's say this specific kind of Simulink, you click the button, you get the controller, you put the controller in the car, right? So AADL, it is a little bit more specific than SysML, but less specific than Simulink. It is oriented for the software and hardware real-time system, interfaces with analytical tools. It supports model-based system engineering toolchain like TASTE, well accepted in avionics and aerospace, but actually mostly on these domains. It is very specific. You cannot, let's say, you could use it only for what it has been developed, like for the software, hardware, real-time system architecture. And it is relatively poor, I mean, relatively to UML or Simulink, poor tool support. It's basically 108 plus a couple of the commercial tools which are not really freely available. Okay. There are other paradigms, automation ML. Automation markup language is a neutral data format based on XML for storage and exchanges for plants, like for industrial plants. And AADL, it is, they took a ADL and domain-specific language using meta-modeling constructs such as classes, attributes, blah, blah. It is based on the concepts from UML, SysML, and AADL, but adapted for automotive needs, and it is compliant with the AutoSAR. It is a special standard in the automotive. Let's say it's just kind of the mixture, but mostly based on the AADL. Okay, conclusions or some takeaway messages. Cyber-physical system currently is active or hot research and development domain. It's continuously changing. There are new versions of SysML, new versions of AADL, MATLAB, everything something new. So, and the paradigm of the cyber-physical system is also changing. It evolves over time. There is no silver bullet. I cannot say, okay, guys, in your system you have to use like SysML using this guideline and it will, and everything will be good. No, that's why exist different methodologies or different paradigms. Usually the guys are using them even together. Like on the top level, you design something with UML and then you use Simulink to describe some controller logic and you use some AADL to describe another controller, or like on a more top level, and then you use some Simulink state machine to describe the logic of something else. So you could combine things. So, and there are lots of players, I mean, the industrial players, the certification bodies who defining the standards, defining the tools and so on. And some places they are competing and some places they are collaborating. Okay. So basically that's all for today. Something is saving. Good. I just decided this time to go, you know, from the beginning to the end. I leave all the questions to the very end because I wanted to be in time, and I already eaten like 1 hour and 30 minutes, so have to finish. Okay, guys, if you have some questions, let's discuss them now. So just open your mics and let's do some discussion. Or if not, we should agree on the next lecture when we'll do the next one. Are you here?
Yes, we are here.
Okay, so I don't hear questions. Let's do the following. Let's agree on the next lecture. When we'll do the next lecture. Let me stop the screen sharing. Stop the recording.